Okay, a couple quick things, reminders.
Oh, the power output is the weight.
Okay, so remember we talked about, remember the day we talked about buying trucks, about how, what power does?
So that number is force times displacement. And it's force, so it's, go through a couple things.
And we talked about pickup trucks and power, right? Torque is the amount of force you can apply to the road, twisting force on the axle essentially, right? Power is how fast you can do work, right? So power, definition of power, quick reminder. Power equals the rate of change of work, right? It's the amount of work you can do in a certain amount of time, right? Well, now think about, there's an interesting way you can, so for example, if let's say that you do 100 joules of work in 10 seconds, how much power have you exerted? What's the power rating of that? 10, and what are the standard units? Units of power. Are watts. 1 joule per second equals 1 watt. And we just abbreviate that with, it's a little confusing because it's a capital W, just like work, right? But you know that when it's in the context of a unit, it's a watt. Okay, so if it's a rate at which you do work, what's work equal to again? What's the definition of work?
Force times distance.
Force times distance. Okay, so we could say that's the same thing as force, right? Work is force times distance over time, right? Okay, so what if it's a constant force? If it's a constant force, we could write that as force times distance over time. And what's distance over time?
Power.
Distance over time.
Oh,
Rate of change of velocity, yeah. So, well, speed, right? So it's equal to force times speed in the case that it's constant. Another way to think of it, right? Does that make sense? So if you can, another way you could do this, if you can pick up a 1,000 Newton object and you can pick it up at 2 meters per second, well then you know that's going to be 1,000 newtons times, it's all standard units, 1,000 times 2 is 2,000 watts of power. Okay. Does that make sense? If water is flowing, let's say water is flowing over a dam. This is kind of interesting too. Let's say water is flowing over a dam so that, let's say that 1,000,000 newtons of water is traveling 1 meter down. So it's traveling 1 meter down, vertically down as it moves over a spillway. It might move further along the spillway, but it's going vertically down by 1 meter in, let's say, 2 seconds. Actually, 1 meter in 1 second. So it's moving down at 1 meter per second. What's the potential power output of the dam? 1,000,000 watts. Yeah. Are you gonna get all that out of it? No, you're not. Because you're not gonna be perfectly efficient in harnessing that power in the turbines, but you're gonna get a certain percentage out, right? So you can see, you can see why hydroelectric dams are they work so well. There's a lot of heavy water that's naturally wants to go from high to low elevation, right? And all you're doing is just harnessing some of that energy as it rolls through there, right? And so there's big power output. So that's why we have amazingly cheap power in the Northwest because of all our hydroelectric dams. Are there potentially cheaper ways of doing that? Yeah, there's some sort of large scale experiments going on, and this actually people are starting to do this a little bit with like tidal dams, where you could capture as the tide comes in and goes out, you could capture a lot of that energy by either turning turbines just into currents or by actually capturing it behind a wall and letting the water back out. And that's obviously, there's just a lot of available power there. There's engineering to do to get to that point, but same principle as a hydroelectric dam. Okay, so there's power. What did we say about pulley systems? Or block and tackle? What's obviously, I mean, the actual mechanical advantage is always the same. Output force over input force. Input force is what you're applying to the pulley system, output is what it's actually lifting. But what's the ideal mechanical advantage? What did we say about that? Oops, what do you call it?
Ideal mechanical, the input over the output, instead of.
Right, I mean, it's always gonna be input distance over output distance, but there's a really easy way, you can look at a pulley system and immediately determine what the theoretical or ideal mechanical advantage is.
It's like how much,
Or how many like loops or how many chains?
how many times.
Okay,
the
how many
pulleys-
lines are attached to the load, right? Does that make sense? So how many can you count? How many separate lines can you count that are attached to the load?
That's only counting them like for one direction of travel or
Right, so like, for example, in this case right here, if you've got say you've got there's the ceiling, and you're gonna do something like this. There's another pulley, and you're just gonna pull down there. What's the mechanical advantage? Theoretically, two. It's two, because you can count 1, 2 lines attached to the load, right? Sure, they're both going to the same pulley, but it doesn't matter. How many lines can you, and what if we add one more up here? Let's say we're gonna add another pulley up here. So it goes down there and then that attaches to that pulley. 3, right?
So
Yeah,
basically how many pulleys there are.
It's not how many pulleys there are, it's how many lines there are attached to the pulleys. Because like this would be 2 pulleys, but I've got a mechanical advantage of 3.
Upstream of the first pulley. right?
Yeah. See what I'm saying? Yeah, this one doesn't contribute anything. What's this one? All it does is changes the direction of the pull, so we can pull down instead of having to pull up. Right? Okay, so number of lines attached to load. What's the theoretical mechanical advantage for a wheel and axle? Remember, that's the one we said it's almost just like it's just like levers, only the levers are continuous, right? It's like an infinite number of little spokes that are act as the levers. So what do you think? Like, I'll draw you a picture. So tell me, for this wheel and axle, let's say, how am I gonna calculate? So I'm pulling on this line, and it's lifting this load. What's it gonna be?
On the proportion, the smaller the part
The radius, right? So we'd say the radius, that's what we'd call right there, that's gonna be the input radius, isn't it? Right? And this is gonna be from there down to there. That distance is the output radius, right? It's always gonna be the ratio of the input radius to the output radius. So this is a mechanical disadvantage, right? This would be one where you had an excess of force that you wanted to pull something up really quickly, right? Okay, make sense? And the way you can kind of look at that that's convenient, remember we said that if you do, I'll draw better circles. So think of it this way, right? If we've got, let's say we've got a lever, this is like the fulcrum on the lever. Right? And if this is where the line's coming off, let's say that we're pulling on the line. Here's the line that's coming off, and we're gonna pull down on that, and it's going to pick up a load right there, right? Isn't that the same thing if we think of this as being a lever, as applying an input force there, and that's lifting up an output force, like a load, right there? Isn't that cool? Right. So you can see it, if you just look straight on, that's really all the wheel's accomplishing. It's just an extension of those levers, isn't it? Only remember, if we tilt this lever, then the lever goes away, but the wheel, just a new, just a new part of the wheel rolls up, and so the wheel always maintains that same distance, whereas the lever wouldn't, right? Levers only get to, with a lever, think what you'd have to do with if you're prying something up, you gotta push down with the lever, jack it up, push down again, right? With the wheel, it's just continuous, right? As long as you're pulling on this side, it's applying a force in that vertically upward right there, right? Okay, make sense? All right, go. You got it.
Did you talk about the trebuchet arm, Mike?